In example number 3, we want to solve the equation y prime, which is equal to x squared y. So we're going to first rewrite the equation using Leibniz notation. So we're going to rewrite y prime to be dy over dx, which is equal to x squared y. So we're going to have to divide both sides by y and then multiply both sides by dx. Now, if y does not equal 0, which we do not want it to be 0 since it's in the denominator, then dy over y is going to equal x squared dx, where y does not equal 0. Now over here it states that if a solution y is a function that satisfies y of x is not equal to 0 for some x, well, it follows from a uniqueness theorem for solutions of differential equations that y of x equals 0 for all x. Okay, now that we've done that and got our y's on one side, x's on the other side, we're going to go ahead and take the integral of both sides. So the antiderivative of 1 over y dy is the natural log of the absolute value of y. And that's going to equal the antiderivative of x squared, which is x cubed over 3 plus c. Now, this equation defines y implicitly as a function of x. But in this case, we can solve explicitly for y as follows. We can rewrite this using properties of logarithms like we've done in the first example of section 7.3. We would then have the absolute value of y, which is equal to e to the natural log of the absolute value of y, which would then equal e to the x cubed divided by 3 plus c, since we know that the natural log of y equals the following. So we're replacing the natural log of y with that exponent. And then we can rewrite this in terms of e to the c times e to the x cubed over 3 by using the properties of our exponents. And then because this is the absolute value of y, y would then equal plus or minus e to the c times e to the x cubed over 3. Now, we can easily verify that the function y equals 0 is also a solution of the given differential equation. So we can write the general solution in the form of y, which is equal to a e to the x cubed over 3. And the reason why they write a is because that's going to represent the constant that's being multiplied by e to the x cubed over 3. So a would be an arbitrary constant where a is equal to e to the c, or a is equal to negative e to the c, or that a would equal 0. Now if we take a look at figure 3, which are these right here, figure 3 shows a direction field for the differential equation in this example. And you can compare it to figure 4, in which we use the equation y is equal to a e to the x cubed over 3 to graph solutions for several values of a. So if you use the direction field to sketch solution curves with y-intercepts 5, 2, 1, -1, and -2, they will then resemble the curves found in figure 4.